Good evening, and thanks for taking the time to attend this webinar. As you can see from the title of the slide, this webinar is going to demonstrate some microscale chemistry practical activities, the equipment used, and how it can be used to teach chemistry concepts to students, whether in class or using remote teaching using the internet. So why perform microscale chemistry? Well, it's safer. The definition of microscale chemistry I'm going to use is we're using small quantities of chemicals and fairly simple basic apparatus, as you'll soon see. So the advantage of microscale chemistry is it's safer. You're using smaller quantities of chemicals, therefore you're releasing smaller quantities of gases and so on, and practical time is reduced. When I first started teaching science, I tended to underestimate how long it took to do a practical lesson. When you think about the time it takes to give out instructions, fetch a test tube rack, put the test tubes in the rack, add the chemicals and distribute the chemicals, then the pupils analyze and record the results, and then they have to rinse and clean the test tubes and then put them back. This was all very time consuming. With a few dropper bottles and a laminated sheet with instructions on the sheet to help focus it so they're not, and this is one advantage of microscale chemistry, is that the instructions can be in the sheet and they don't have to grab another sheet or look at instructions on a projector screen to do the experiment. So time can be probably used more efficiently with microscale chemistry for certain practicals, leaving more time for observations and questions. The reduction in preparation time, cost, clearing up and disposing of waste is more economic, efficient and environmentally friendly. And with the technology available now, such as this, demonstrations can be done online like this or projected onto a screen for students. And one of the main advantages of microscale chemistry is a laboratory is not required. It's portable. I can go to primary schools or do outreach in various places that don't have a laboratory. And one example of this would be at a Science and Stage conference. So I first got to know Bob when I was presenting a project in Hungary in 2017. And what I needed to do was some kind of distillation, but I didn't have access to a sink and I didn't want to bring expensive apparatus. And Bob and Mary Owen of Cleeps came up with a microscale distillation method that I could do to distill orange oil and lavender oil to people that visited my stand. And this was based previously on an idea from Chris Lloyd at CERC. So that's one of the advantages. And I saw this other stands at Science and Stage in 2017. So other stands, ones from Hungary, use blister packs, from pill packs, if you like, to do microscale chemistry demonstrations. Eva Doboni Tarai from Hungary did reactions by injecting hydrogel beads, which act as a kind of magnifier to do microscale chemistry as well. And the more recent Science and Stage conference in 2019 in Portugal, you can see that there were stands in Portugal and Belgium that were doing microscale electrolysis using 9-volt batteries. And there was a workshop done by Nasko Stemanov of Bulgaria demonstrating a portable microscale chemistry kit he could use in various schools. So one advantage of microscale chemistry is portability. You can go to an international meeting without too many hazardous chemicals and present fairly elegant and good chemistry overall. So traditional apparatus is shown on the left here. So rather than using test tubes, power packs, Bunsen burners, tripods and crucibles, which can be expensive and require you to order them from specialist science suppliers, microscale chemistry can use laminated sheets, 9-volt batteries, spirit burners made from jam jars, which I'll show you later, and bottle tops, which you can use as crucibles. And these are cheaper and easier to obtain. So probably a main game changer for microscale chemistry was the digital technology which you can use to present it. So the videos I'll be showing will be using a document camera visualizer like the one shown on the left here. And Bob has done nice microscale electrolysis experiments using a fairly cheap USB microscope to focus in on what's happening at the electrode and drops as well. So a visualizer, so this is very suitable for webinars like this, socially distant classrooms, and for teaching a live or recorded lesson during a pandemic, as I've had to do over the last few months. So a visualizer, a USB microscope, can project experiments onto a screen whether it is in a class or in a live online meet. And pupils will always have smartphones with them these days, and they do ask us sometimes video experiments or take pictures, and I think this is good for engagement. They can show them to their parents and get them engaged with the science that they're doing in class too. The first demonstration I'm going to show you is one I've done for younger pupils that helps introduce them to chemistry. So I'm talking about pupils that are maybe visiting the school that are about 10 or 11 years old before they come to our secondary school. This is an escape room puzzle in which they have to do some microscale chemistry experiments to open a locked box. So the article, more details in the article that I've shown here on the slide, but I'm going to show you a video of the experiment. Okay, so this video is going to show you the puzzle. So I've got a box here with a padlock, and the aim for the pupils is to try and figure out what the code is to open the lock. And they have to do some microscale chemistry experiments to open the lock. So you can see I've got a laminated sheet with instructions. The pupils are given dropper bottles. Dropper bottles I recommend for doing this kind of thing rather than dropping pipettes, because you'd have to rinse out pipettes that could get contaminated. So everything's nicely contained in here. You can imagine having to set this up with 8 test tubes and so on. So the first reaction you're looking at here is a precipitation reaction. And you can see if I add the lead nitrate to the potassium iodide, we're getting a yellow precipitate. And this introduces chemistry to the students that we're forming a new substance, a new solid is being made. The next experiment involves fairly dilute acid, hydrochloric acid. It's at an irritant concentration, about 0.1 molar rather than a corrosive concentration. And to this, I'm adding some universal indicator, which will give a red color overall. So this introduces pH. For younger people as well, the names of the chemicals can be quite intimidating to them. So it's a literacy exercise for them that they can follow instructions and add the correct chemicals and get the correct result, especially when they're first coming to a science classroom. The next experiment involves adding dilute copper sulfate, a transition metal, to dilute ammonia solution. And this is going to form a transition metal complex. So after this type of activity, you can tailor any recap according to the level of the students. If it was younger students, I would talk about how do we know it's a chemical reaction? What are the signs of a chemical reaction? For older students, I would talk about precipitation and ions and lattices. And you can go as far with older pupils and talk about transition metal complexes, splitting of D to D orbitals and absorption of wavelengths of light to give a color and so on. The final one is one that's typically used for titrations. We've got some sodium hydroxide added to some phenolphthalein. Now, the advantage of this experiment overall is that the cleanup, the dropper bottles get collected and put away, and the sheet is rinsed down the sink very quickly with some water and wiped with a cloth, as opposed to having to wash out lots of test tubes with a test tube brush and put them in a rack to dry. So you can see that the pupils have now done if they've done the reactions correctly, they will get the code, which is 3157. And they use this key at the bottom to get the correct code. So once the students have got the correct code, then they can open the box that you're going to see next. So the scenario I use for this is they've been infected with some kind of poison or venom, and the antidote or the cure is in the box, and they've got a certain amount of time to do it. I usually do this in combination with 5 other puzzles. So once they get the code, the lock can be opened and they can get the reward, which the reward antidote usually looks like something that's pleasant for the students to eat or taste. You can do you can make digital codes. They could have a code to unlock on their phone or their laptop or their device if you don't want to necessarily use boxes and locks. So after you've got the pupils to identify signs of reaction, such as color changes, you want to identify other signs that a new substance has been formed. So if you add magnesium to a drop of 1 molar hydrochloric acid, the pupils can see quite clearly that we're going to get a gas produced. And if you ask pupils what gas is produced, they will tend to say carbon dioxide, just because they associate carbon dioxide with fizzing and the bicarbonate soda and vinegar experiment. So you really need to get the pupils to think about what's reacting here. Magnesium with hydrochloric acid, that's the elements, and their gas being produced is hydrogen gas in the reaction. So this is another sign of reaction. Now, we can take this a little bit further by comparing the reactivity of different metals to get a reactivity series. So I've got tiny pieces of copper, zinc, and magnesium added to a drop, and I'm moving it with a wooden stick. We call them cocktail sticks. I'm not sure what you call them in other places. And you can see that the magnesium is the most reactive metal. It's fizzing quite vigorously and producing hydrogen. And on the left-hand side of the zinc, we're seeing some hydrogen being produced. So they can come up with a reactivity series of magnesium, zinc, and copper in order of reactivity. Copper won't react with dilute acid, but you can react with more concentrated acids in a Petri dish in a small scale to generate nitrogen dioxide, of which you can test the pH using some pH indicator. The next experiment is coming up, which I think is the iodine clock. So iodine clock is one of my favorite demos. You have sodium metabisulfate plus starch added to potassium iodate. And what happens is the iodine is released all at once and reacts with the starch in a moment or so to form a blue-black complex. Now, this is one good thing about microscale chemistry. You can take large-scale demos and shrink them into small drops, and with the visualizer, almost get the same effect. So this is a microscale iodine clock. So I'm adding some potassium iodate to some sodium metabisulfate and starch. And what I like about this is some people will immediately come to you, "Oh, it's not worked, sir." And then I say, "Go back and look," and then they'll see this happening. And what I like about this is that I've not mixed it properly, and you get these little parts of the reaction occurring at little nodes or drops here. So it's a slightly different effect, not so sudden, and it's a little bit more elegant and interesting to look at. So you've got to tell the people sometimes reactions are a bit slower and you need to observe what is happening and not go rushing off to me and saying it's not worked after adding two clear solutions. Now, of course, this can be used to look at the concentration, effective concentration and rate of reaction. So if I take 3 different concentrations of potassium iodate as shown here, and I add the sodium metabisulfite and starch to it, you can see which one is most concentrated, because the one on the left starts to change color, followed by the one in the middle, and finally the one on the right. So now you can do quantitative data on rates of reaction as well, but you need to probably do it in a slightly different vessel from a laminated sheet. So in this experiment here, the rate of reaction can be measured by adding hydrochloric acid with various concentrations of sodium thiosulfate, which is just done by adding different numbers of drops and making up to the same volume of water. This will generate a cloudy solution, and this is done in a plastic cell plate you can see in the top right. You can get them from specialist science suppliers, but if you know somebody who works in university and does cell culture or ELISAs, you could probably get them for free from there, or use ones anyway. So basically, the reaction time is measured by the time it takes for the solution to obscure a cross drawn underneath the plate. And the reaction rate is determined by dividing the reaction time, 1 by the reaction time, I should say. When the rate is plotted against concentration, it gives a reasonably good straight line, as you can see. And note that the 2 points that are at the bottom at 5 and 10 seconds are maybe the least accurate, because that's the slowest reactions that give a more gradual change. So accuracy can be talked about in terms of measuring the rate of reaction as well. So you can see a real progression in learning in these experiments, starting from signs of a chemical reaction, comparing the rate, and then measuring the rate of reaction using fairly easy to do experiments. So that's my first part done. So I'm going to hand over to Bob, who will do the second part of the webinar.
Hello, and welcome to the show. That's really nice, Adrian. I like that. Anyway, I thought I'd just show you the plastic sheets and the instructions you kind of do. So here's one that I've done on identification of negative ions. And it fits into a wallet like that. And that's what we do the reactions on. And it works because water and plastic, the plastic surface doesn't interfere with the hydrogen bonds within the water. And so you get really nice little hemispherical puddles. There's one other piece of equipment I would like to show you, and that is the conductivity meter, which I should be using. And we're quite advanced with some of this material. These electrodes here are not graphite. These are carbon fiber, and they're extremely strong. They don't break. They're not breakable by the students. You have to do a bit of soldering to make that version, but I recently came across a version like this from Germany, and they make their connections using these connection tubes here. And there's the LED in there. And you'll see more about this when we start the video. Okay, so yes, so what we're going to see is everything happening in puddles. And I came across these types of reactions because through my job at Cleeps, which is at the back here, we deal with all the safety in school science and design technology in England, Wales, and Northern Ireland. And Scotland have their own organisation called CERC, which Adrian referred to. And we address any sorts of issues that appear, such as when the whoosh bottles first came out, we wrote a very precise method of doing it, and woe betide you if you don't follow it and something goes wrong. It also, as Adrian pointed out, has green credentials and reduces the costs of equipment and materials and disposal. There is a move from South Africa with John Bradley, who produced a kit that went out to the people in the remote schools there, so they could carry out some practical work in their ordinary classrooms. And so it was producing practical science in developing countries, because this was taken up by UNESCO and went all around the world. Well, these were quite satisfied. I was quite satisfied with these 4 points, but there was more to come. So what we're going to have a look at is one of my opening experiment, which I carry out in my workshop, which unfortunately I've not done for a year because of this horrible virus. So here we go then with putting, there's the sheet, and I'm putting buffers down the columns of each down the sheet. Then I go across with the indicators, and these are right. Just stop there. And the first indicator was bromothymol blue. The second one is methyl orange, and the third one was phenolphthalein. And buffers are 1, 4, 7, 9, and 13. Now, if you make a mixture of these buffers, and that's where the in the next column there, you make a mixture of these buffers, see what happens. And you get a universal indicator, which you can compare with the commercial version. Recently, during the pandemic, a group of us have had a little bit of fun working out doing some work on the colours of natural indicators. So this is the red cabbage one that you all know, and there you see red cabbage normal, and you can see how it varies with pH. Not only that, you can see that there's a change with metal ions as well on the bottom there. And the Tradescantia leaf, they're all fantastic. And you can go through the whole year trying each these flowers. It's a really good lockdown project, that is. Okay, so this is the conductivity indicator, and there is the way it's set up. You have to have a resistor in the circuit. That is to stop the LED from burning out if there's too much passing through. There's a link here to a YouTube channel which has got some rather nice practicals. And what I want to do is to test this with tap water and distilled water. Now, this is London tap water, which I'm putting into the circle. And when I apply and that is real. That is our tap water in London. Pretty hard stuff. And if we compare this with distilled water, then And the next there, we see as we attach the electrodes, no light at all. So you can actually tell the difference between different different types of water. And this is rather beautiful because now we can do some work to see if we can look for ions in water. And so yes, there's nothing happening to the LED. Now I'm going to put in a pointed splint. I'm going to pick up a tiny crystal of salt, and we'll see what happens as I put this in. Now, I want you to compare that with the indicator, with the conductivity indicator, which is on the other side. And you can see now that that LED is lighting up. Of course, we can look at ionic and covalent compounds now by looking at white sugar and soft brown sugar, the molasses. Now, white sugar is sucrose, and of course that is not ionic at all, so it doesn't light up. But when you start to look with brown sugar, you just see the light beginning to appear. So there are impurities in brown sugar which have form ions in the water. And look at the lovely light in the salt now. We can look at things like diffusion. This is a time-lapse video, and I've put the indicator in, and I just need to stop it there because I was quite surprised at this. It was this was taking around about 3 minutes all in all at this point. But look how the purple color has moved towards the positive electrode. That was quite a surprise to me, showing that the permanganate anion has a negative charge. So carry on with that. This takes a little. So we can study diffusion and see the path of water through the puddle. You can also see it gets kind of a stronger purple around the positive electrode, which is on the right as we're looking at it, and there's the colour is less pronounced around the negative electrode, which is on the left. And of course, bubbles start to appear as we actually go. If you put universal indicator into tap water, and you can put the indicator, you can see these wonderful colours coming up. And look at that. Around the red, you've got the yellow, and round the blue, dark blue, you've got the light blue there. And you see reactions occur. Remember, for a substance to conduct electricity, electrolysis has got to happen, and it is not a lot of others that is made of. Well, this is my final video of this section here, and this time I'm putting tin chloride in. Well, I was surprised at this because all the textbooks tell me that tin chloride doesn't dissolve in water. I've got to add conc hydrochloric acid to it, but you don't. You just put the solid in. The solid dissolves, and then something starts to happen, and bubbles start to appear at the electrodes. Now, the bottom electrode is the negative electrode, and suddenly you start to see the fantastic crystals of tin appearing out of the electrode. What amazes me is if you look at the if you look at the bubbles, they're kind of moving between the electrodes. I've not really found a reason for that. Is there electric fields or something? Oh, and then you get these wonderful branching patterns as well. Towards the end, as the tin begins to get less and less concentrated, you see bubbles coming from the tin, and these are competing reactions that occur in electrolysis. So electrolysis is quite a complicated business, really. There it is. I just okay. So there we have it. So these were the extra things I found as an advantage to doing microscale. The classroom management. Notice we sit down to do all these experiments, which makes management quite easy. Now that may conflict with some rather regimented rules that you might have in laboratories, where you've just got to convince people to do it, and because you've got to have the control, and it does focus the attention of the students better. And they're over so quickly, you've got more time to teach and explore some of the intricate aspects of some of these reactions. Well, we'll have a look at some of the other things later on. So I think we'll leave it there and pass it over back to Adrian. Thank you very much.
Right, thank you, Bob. I use the electrolysis setup as well. I've done it on online lessons live and recorded with my classes, and it's a great way of showing electrolysis, and it generates low amounts of chlorine and toxic gases as well. So it's a nice, easy thing to do as well. Okay, what I'm going to show you is how to make a spirit burner to do heating experiments in rooms that don't have a Bunsen burner or access to gas. So you take a jam jar that you would get from a hotel or a cafe, and a bit of string, and you basically put some ethanol into the jam jar, and I'm soaking this bit of string into the ethanol to make a wick. The lid has had a hole drilled through it, and is held together by glue, and there's another hole in there to let some oxygen in to burn. So it's just a case of lighting it with a match, and you have a burner that you can do reasonably elegant heating experiments with students that you can video or demonstrate in front of a class, or even get the students to do themselves. So the first experiment I'm going to show you is ones in which I'm going to use bottle tops to heat ionic and covalent compounds to show the differences in melting points. When you use bottle tops, make sure you burn the plastic inside off first, as you can see in these experiments. So this is speed up. I'm just going to pause this. So I've got sodium chloride and copper sulfate, which are ionic compounds, and glucose and wax, which are covalent molecular compounds. I'm not going to cover networks. I leave them to later. But this is a nice experiment that you can do, or the students can do, in which you see the ionic compounds don't melt upon heating in a spirit burner. But if you take covalent molecular compounds, such as glucose and wax, they will melt quite easily. Now, it's important to do some kind of modeling at the end of this, because the students will get the misconception that you're breaking covalent bonds when you're melting covalent molecular compounds. So really, it needs to be followed up by examples using models and descriptions on a board and so on to show clearly that intermolecular forces are being overcome when melting covalent molecular compounds. So you can also use this to look at the number of moles present attached to copper sulfate. So this is taken from a sparkling wine top that is the wire attached to it. And I've made this into a little tripod, which I'm going to put on top of the spirit burner. So you can, this is a kind of makeshift tripod. And we're taking hydrated copper sulfate in a bottle top that's had the plastic burnt out. And what's happening here is the bottle top with the hydrated copper sulfate has been weighed beforehand. And as we heat this, the water molecules are going to be evaporated off of the copper sulfate. So you can see the color is changing from a blue color to a kind of off-white color overall. At the end of this experiment, they would weigh the bottle top and do some mole calculations to figure out the amount of moles of water lost and therefore attached. And generally, most times I get round about 5. If it's been less than 5, it's probably because I'm using copper sulfate that hasn't been fully hydrated. Now, there are additional advantages of using a spirit burner for this experiment. It works fine without a desiccator, and you don't need crucibles. The time is quicker. But copper sulfate with 5 water molecules attached loses 4 of its water molecules at a temperature about 100 degrees Celsius, and it loses its final water molecule at 150 degrees Celsius. If you get the pupils to zap it in a crucible at very hot temperatures at 650 degrees Celsius, this can cause the copper sulfate to decompose and release gases that you wouldn't want, like sulfur dioxide. So as well as being hazardous, this decomposition can affect slightly almost improve the accuracy of the results. So using the cooler flame of the spirit burner helps prevent this decomposition. Now, by accident, we found that when pupils were heating copper sulfate in bottle tops, sometimes a bit of it would catch a flame and give it a green color. So you can actually do a little flame test by adding a grain of copper sulfate to a moistened wooden stick and get this slightly green color formed overall. And this is nice, tiny, small amounts. So the exposure to copper sulfate is very minimal here. This can also be done with lithium chloride if you want to do it, and various other salts for flame tests. So again, moisten the stick, add a grain or so of lithium chloride, and simple flame tests can be done. It doesn't work so well for things like potassium, but you can get reasonably good colors with strontium and various other salts as well. Now, however, this is quite short-lived, the flame. If you want longer-lived flames to look at the color and maybe a more spectacular demonstration, then this setup is a useful one. I think this was developed by Magda Pollock and Bob Worley of Cleeps. Bob can maybe correct me on that. And this basically involves a bottle top with the plastic burnt out. Onto that is put a sugar cube. And what I'm doing in this video is I'm adding copper chloride, which has been dissolved in ethanol. And I'm basically adding the copper chloride to saturate the sugar cube with ethanol. Once that's saturated with ethanol, then you can light the cube with a match. And initially it's the ethanol that burns. We don't get a color in the flame. But as the temperature increases, we start to see the characteristic green flame associated with copper. So this allows people, and I have had people looking at this with simple spectroscopes. So they can look at, and you can talk about electrons being promoted, and dropping down to lower energy levels and releasing certain wavelengths of light and so on. So they can get spectral emission lines looking through simple spectroscopes from this. It gives a slightly longer flame as well. In addition to this, you can see that a carbon snake is starting to come out of the bottle top. And this is very similar to an experiment you may have seen in which you take some sugar and you put it into a beaker and add concentrated sulfuric acid. And this is a dehydration reaction and is exothermic in nature. And a carbon snake will rise out of the beaker as the exothermic reaction releases carbon dioxide and water, and left with the unburnt sugar, which comes out as a snake, as you can see to the right. So this is a very similar sort of experiment. The sugar's only, I think, providing a kind of fuel for the reaction, which gives it and no two snakes are the same. You can get 3 people to do it, and you get some quite weird and wonderful, interesting shapes when you do this. So one thing to note as well, that the tops of the bottle tops can get quite hot. So make sure you handle it with a forceps, that they keep their heat more than you think. So so this is a nice way of doing a flame test in a microscale method. Make sure your visualizer, if your video is far away, because it can get quite hot as well, and you're at risk of damaging the actual camera. So this is done. You can do this with copper chloride. I've only tried this with copper chloride and lithium chloride, but you can see we've got our little carbon snake in the bottle top there. So the next video I'm going to show you is going to be speeded up. It's got lithium chloride. So you can see you get a characteristic red flame with the lithium chloride as well. So it's a nice example of a flame test to do. And you see that the carbon snake comes out in 4 different directions in this one. So, and forms a kind of sticky caramelized toffee there as it comes out. So it's a nice one for the students to do as well. It's relatively safe. So I'm just going to pause this. So this is an advert for a detox foot bath you can get in Amazon, and they cost about €300. And I tell the pupils that they can save a bit of money by doing this microscale. So you can see that there's a before with clean water and an after with brown water. The brown water is meant to represent the toxins from the detox process that are diffusing through pores in the skin into the water. And people have come up with color charts for this, like so. So you can see that if it's brown, that's purifying the liver. We've got tobacco and debris coming out. And if it's dark green, it's purifying the gallbladder and so on. So what I tell people is that we're going to do this microscale to try and save a little bit of money, because €300 is a lot of money for a foot bath. So here's the setup. We've got 2 iron nails in a used cheesecake dish. I've added water to it from my tap here. This is done at home. And I'm adding some salt to it to make an ionic solution that conducts, that completes the circuit. So we're forming an electrolyte, as it were. Now, to do our detox, we're going to need a volunteer. So my unwilling volunteer for this is somebody who's found lockdown a bit tricky just now, which is Barbie. So Barbie's kind of, I think, been a little bit bored and maybe not been looking after herself too much. So her feet are in the foot bath, and then we're going to complete the circuit using this 9-volt battery. So we're going to look at a speeded up, close-up version of what's happening to the dish now. And bizarrely enough, I've got a collection of dolls that the pupils do this with at separate benches overall. So this has been speeded up. So I'm stirring it every 30 seconds. But what you can see is that during the detox process here, the ions are coming out of the feet into the water and generate a slight off greeny brown color, as it were. So, and then people start scratching their head and thinking, well, why isn't a so-called inanimate doll being detoxed, and what toxins are coming out of the doll here? So you can see that, and you can do this within about 2 or 3 minutes. It's quite a quick experiment to do. So the feet are going to come out in a moment or so, and you can see that Barbie has been fully detoxed. The toxins apparently have been diffused out of her little legs. So is that the case? Well, this is the experiment repeated, but this time I'm going to add something called peroxyl indicator to the solution. So this is potassium hexacyanoferrate and phenolphthalein mixed together. And basically, if it detects Fe2 positive ions, it will give a blue color. And you can see the bottom electrode, which is the positive electrode, is giving a blue color with the peroxyl indicator. So why is it giving a blue color? Well, the positive electrode is removing electrons from the iron nail. So we're getting an oxidation reaction here. So we have iron atoms changing to iron 2 positive ions. Note the visualizer is useful for this. I can annotate experiments in real time with students online or recorded for ones that are absent or have internet problems. There's a further stage of oxidation which occurs, in which the iron 2 positive ions lose another electron to form iron 3+. And what the iron is doing is reacting with the oxygen to form the compound iron oxide, Fe2O3. And then the penny suddenly drops to the pupils once we've done a little bit of corrosion, is that people are paying £300 for a detox water bath, which is generating iron oxide, which is basically rust. And that when the penny drops and they realize it's not all what it seems, it's a nice moment for them when they realize this. So what's happening is the positive electrode is removing electrons from the iron nail, causing it to corrode and form rust, while the one at the top is protected from rusting because it's been supplied with negative electrons at the negative electrode. So this is there's lots going on here. There's oxidation reactions, there's indicators, there's all sorts of nice chemistry going on here as well. So I kind of like this experiment because I think it helps pupils use the science that they've learned in school to critically evaluate the science they will come across in real life, and maybe even it might save them a little bit of money as well in things that are not what they seem. I think this is important in this particular time because there's a lot of misinformation about vaccines and COVID-19 at this time. So it just allows the pupils to maybe critically evaluate the science they're seeing, especially if it's from characters that might not be so trustworthy. So with that, I'll hand off over to Bob for the final section of the webinar.
I love the little flame test. It's really nice. Now, let's have a look at some old reactions and give them a new look. So I finished my section with a list of the things which I think are quite important, and what it brings to doing some new chemistry. But there are some negative observations as well, and I think the one that affects us most in the UK is that some teachers feel that their students are at a disadvantage if they carry out new procedures, even though they might provide better information and evidence. So we do have a resistance to any sort of innovation in this country. Certainly in England, it might be different in Scotland. Anyway, so let's have a look at some rather interesting ways of doing things. Now, this is a new look at precipitation. I'm wetting my little bits of stick, and this is distilled water. And I'm now going to put in silver nitrate and potassium iodide from either side of the puddle. Now, often we just supply solutions to students, and they just mix it together and the magic happens. This time they are making the solution by using the solids. So they're seeing where the liquid, the solutions are coming from dissolved solids. And then in the middle, we get the precipitate of silver iodide. And you could talk about dissolving, solvation, diffusing, and what have you. This is an example. We can go into a thing called the Alex Johnston triangle here. We tend to overload our students quite a bit with complexity, and they all enjoy the macro events, even to Barbie having a detox. But it's when we kind of do the nano interpretations and symbolic and mathematical approach to chemistry that we tend to lose them. So Alex Johnston produced this triangle. It has been increased in points from 3 to 4 by Peter Mahaffey in Canada, who produced the human element. Well, I don't really like using the word element in this context, so I tend to call it the relevance to students' lives. And we come across precipitation in the purification of our drinking water, precipitation of calcium carbonate in the sea, making pigments, medical science, you can get kidney stones, and every morning students will wash themselves in soap and form a precipitate in the water. So we could make it, we could look at that sort of thing. Now, we could do a little simple modeling here, and this is done with PowerPoint. So in go the crystals, they dissolve and solvate, and then they diffuse through and form the precipitate. And you can see there where those pesky spectator ions come, which we're supposed to learn about now. So there we have a new look at precipitation, and there you see the final PowerPoint slide. We can do the same thing with complexes. This is the iron 3 nitrate potassium thiocyanate complex. And I always remember doing this, projecting onto a very, very large screen at St Andrews University in Scotland. And there were gasps when this slash of red caused by the iron 3 thiocyanate complex formed. Now, interestingly enough, but underneath this puddle, there is a neodymium magnet. And see what happens now. The precipitate is deformed. And the magnet has an effect on the ions. When I found this, I took it to my boss and I said, look what I found. I don't know what the use of this is. And he said, well, Bob, you know, ions are twisted and bent by magnetic fields in mass spectrometry. So I think, oh, well, perhaps I've done something right. Anyway, here we have looking at redox reactions, this displacement, and this is a time lapse, of course. It doesn't happen quite as quick as this. It's not too bad. It's about 4 minutes all in all. And there we see the silver growing out of the copper. It's absolutely beautiful. And there's a kind of blue hue that forms over the copper. You can remove the copper wire, add ammonia, and you'll get a blue solution because the copper is dissolved. These are I'll stop it at this point just to explain this one. So what I'm doing is the 2M ammonia here is going to produce ammonia gas, and that's going to diffuse within the Petri dish into copper sulfate, zinc sulfate, and 1M hydrochloric acid with some universal indicator. And as you see there, the diffusion occurs. So we've got to explain the diffusion of gases, and you can see now diffusion is taking place inside the hydrochloric acid. The outer part of the puddle is going alkaline, and the inner part is still acidic. So the reaction is gradually moving through the puddle. Very interesting. I can do this with quite toxic gases, with the nitrogen oxides and sulfur dioxide as well. And with sulfur dioxide, you can put it through into barium chloride solution with peroxide, hydrogen peroxide, and some without. And with the hydrogen peroxide, you get the white precipitates. And you can connect that with the formation of acid rain. This is the formation. This is doing the reaction on a thermochromic plastic, and you can see here on the left the kind of we start with a temperature at this the cold end, and as the temperature rises, it goes red to yellow to green to blue to dark blue, and at the bottom is 2 molar hydrochloric acid. On the top is sodium hydroxide, and you always find that the hydrochloric acid shoots into the alkali in that direction rather than the other way round. It has to do with the ion mobility of the H plus ion, and so you get the thermochromic reaction. This is caused by liquid crystals within the plastic that's at the back. And now, this was amazing. I enjoy watching this. It probably makes me a really sad person, but there you are. But this is citric acid from the right, sodium carbonate from the left, universal indicator solution in water. And it's time. This will take up to about 4 minutes in all. So we have quickened it up a little bit. And I was quite pleased with what I was seeing, the lovely rainbow effect across there. But then, all of a sudden, I started to see bubbles of carbon dioxide appearing. Oh, so there we are. A different look at neutralization. So, just moves on to there, and I'll just stop this. You might be interested to know that we've got some further events, not through Science on Stage, but the Royal Society of Chemistry are producing a conference here on this blue one here, Tuesday the 13th, Practical Chemistry During a Pandemic. Details will be coming out soon. Coupled with this, we're running a poster challenge. So events will come in by the 1st of July, and then we'll enjoy watching these as they come up through the conference. And the day after the conference, I belong to a little group of friends all around the world, and we try to meet every 2 years, and we can't meet this year because of this awful pandemic. So we're having a meeting, and the Royal Society of Chemistry have been so fantastic. They've kind of allowed me to latch this meeting onto the SAFE conference. So keep an eye out for those. And that logo there is for my puddles by the Crocodile Chemist. So watch out for the Crocodile Chemist on Twitter. She has some wonderful pictures, all made with indicators. Now, my website is here. The conference information is here. My Twitter handle is here. I have a YouTube channel with lots of little emails as well. Cleeps have a YouTube channel as well, and this is free to access. There. And if you want to contact me, you can contact me on this email. But I do believe the videos are going to be on available very soon. Just to finish with, because you're getting at it, I thought I would show you this. This. Whoop, I've got a bit. Right. Let's just stop there. Now, there's the neodymium magnet. Okay. This is the first time we did this. It's always the best. It really is. And I did this with my physics colleague at Samir at Cleeps. So we put the neodymium magnet on the back there, cobble it together a little bit, put a bit of do there. We put a puddle in of water, and then we put the universal indicator in. And of course, being a physicist, he likes to go the whole hog and put 14 volts DC through it. I didn't want to do that, but he said, "Oh, come on, let's do it." So, are you ready for the? Well, what do you think is going to happen? Well, let's see. And the colors of the indicators revolve. So I do hope you've enjoyed listening to us. Perhaps we'll watch this as it through. By the way, there's quite a few things we haven't done, and they're on the left there. And if you want to ask Daniel, we put them on at some time. Catalytic cracking, making propene and hydrogenation. We have a voltmeter, electrolysis of copper chloride solution, titrations, more use of bottle tops, equilibrium reaction kinetics. There's no end to what you can do. Yes, thank you very much indeed. I hope everybody's enjoyed it. And listening to two different accents from England, one from from England and the United Kingdom, the Scottish accent from Adrian, and my kind of drony North Midland accent. Thank you very much.
Hi, everyone.
Bye-bye.